without breaking my computer. Okay, Manuel Ceron is the leader of the Columbia Python user group, right?
Yeah.
And now works for Booking.com, and we'll talk about function annotation. Thank you.
Thank you. Okay, good afternoon, everyone. Okay. Thank you. That's nice. Okay, before starting, I'm just going to tell you a little bit about me. I'm Colombian. I'm just now living in the Netherlands. This is my first Europython, also my first Europython talk, of course. I've been programming with Python for almost 10 years now. I know that I look young, but I'm not that young. I'm currently working at Booking.com in Amsterdam. And they told me to tell you that they're hiring, by the way. If you are interested, just let me know. Okay, let's start with the topic of the talk today. So I'm here to talk to you about function annotations. Function annotations. And this is a feature that is kind of hidden or not well known in Python. And that's why I'm here to talk a little bit about this. I know this talk was in the category of intermediate or medium, but I know a lot of Python developers that don't know about this feature. So I'm just going to start telling you what it is, in case you don't already know. So annotations are just small metadata or expressions that you could add to a function definition in Python. In this case, for example, the compile function here can have some strings that describe, like in some sort of documentation, what those arguments are. The cool thing about annotations in Python is that there can be any arbitrary Python expression. So they can be strings, or they can be just an object, or any kind of thing that you can imagine, any Python expression. The second example, just a simple greet function, which is annotated in a different way. Instead of adding documentation to the arguments of the function, we have types, saying what kind of types we expect for those arguments. For arguments, we use just a colon and the annotation. And for return values, we use this right arrow symbol just to describe. These are just two examples of what annotations are. Some things I would like to mention about annotations is that first, they're Python 3 only. They were introduced quite some time ago in 2006. And the PEP is 3107, in case you're curious to see the detailed specification of this feature. Another thing I would like to mention about function annotations is that they're just syntactic sugar. So they're not actually needed, but they're just a neat and clean way of adding metadata to your function definitions. So basically, when you add an annotation to a function, what Python does behind the scenes is just to add this double underscore annotations property to the function. And this property is just a dictionary with your methods and the annotations objects that you put on them. And for the return value, well, you have just return as key. Now, why I'm giving this talk? I just want to tell you a little bit about why I decided to give this talk or to talk about this and to start learning more about this feature, which nobody seems to be using. It's because, well, besides programming Python, I've been using other languages, specifically statically typed languages like C#. And also I've been using a lot of dynamic languages. And something I know that there are some advantages and disadvantages of both approaches. And I like some things of static typing, and I also like some things about dynamic typing. And something I've seen lately during these years in these languages is that you see a pattern where languages are starting to try to get the best of both worlds. You can see that in some statically typed languages like C#, where they're starting to introduce dynamic types. Or they started to introduce type inference, so you don't have to type every type all the time. And the same thing's happening in other languages, especially dynamic languages are just trying to get some of the advantages of static typing. One of the great advantages of static typing is that tools are better with it. With tools, I mean just IDEs or editors, because they can get a lot of information about your code that it's not available on dynamically typed languages. This is just a small example of one language that does this really good. It's called TypeScript, and it's a dialect of JavaScript. It's made by Microsoft. It basically just adds types to JavaScript. And that's interesting because the tools can let you, give you a lot of help about how to do things. And this is just my main motivation for this talk. So we're going to talk a lot about types, but at the end of the talk, I'm just going to mention other uses of function annotations. So let's start with adding typing information to our functions. So this is a small example where we can just start putting types. In this case, we can use directly the object types to our functions. And why would we do this, or why would we do that? As I mentioned before, it helps our tools to make our life easier. Especially, it helps our editors or our IDEs to get information about our code. Yesterday, we saw a very interesting talk about static analysis of Python from one of the guys of PyCharm, and they do a lot to help you with the code. But there are some parts that they just can't help because it's impossible to get information about. With annotation, we can just fill those gaps. Of course, another thing I like about this is that in some way, just it adds some sort of basic documentation to your code. So you can just know a little bit about this, about how what a function expects in its arguments and what it's returning. Now, before continuing, every time I talk about this with my friends or everyone, I just always see some comments about it. And I'm just going to discuss that beforehand. Okay, well, sorry, I just forgot this slide. Before continuing, I just want to mention some things. How can we help our editor or our IDEs? So first, I have three cases here. One is that we have like an authenticate function, and it has this argument called request. And when you type request dot, you expect your editor to give you some hints of what methods are in request. But your editor just can't guess at all. Even a human can't guess at all because request can be anything. Well, you can just maybe guess that it's some sort of request object from your code, but in general, it's impossible just to guess. Another case is when you made just some silly mistake, like the second case, where you misspelled some method. For example, here, we get a user argument and we have a check password, which is misspelled. And of course, that's an error. And the editor can help you with this because you don't know what user is actually. And the third case is when you want, for example, automatic refactoring tools. So suppose that you have this class user and you have this check password method, and you want to just rename that method to something different. And in some IDEs for statically typed languages like Java, you just right-click, rename, and it will just take care of all the cases. Here, for example, in the second case, it would be possible for the IDE to know that that check password is part of that user, so to rename that as well, because it doesn't have the information. So if we start in at some typing information, some small bits, we can help our tools to help us and make our lives easier. For example, we can add just to our request argument, we can add just an HTTP request annotation, and then our editor could immediately tell us all the methods that are available in the HTTP request class. In the same way, if we just add that user is from an object from the user class, an editor can just highlight an error and telling you, okay, you're misspelling something here. And that's what we want to do with function annotations. So okay, well, wait a second. This is something I hear a lot because when I say that your editor can highlight your errors, your stupid spelling errors or something like that, people always say this, okay, you don't actually need that because you have unit tests, or you should have unit tests. And that's true. Well, if you're writing a proper project in Python or any other language, you must have some tests to check that your code is right. And eventually, if you misspell something, well, one of your tests is going to detect that and it's going to fail. And after that, you realize that you misspelled something and you fix it. But this is not the point about this. The point I want to make is that the good thing about having your tools help you is to discover these kind of errors more quickly. For example, if I write my unit tests, I have to just run the test. Maybe I get an error. I have to just go to see what the error is. Maybe if I'm lucky, I can get a stack trace, which point me directly to where the error is. I have to fix it. In other cases, maybe I'm just eating the exception somewhere in the code, and it's not so easy to get just the point where things are failing. And in other words, you have to spend some time debugging and trying to figure out where things are. On the other hand, if you let your tools let you know about these small errors, well, you just get them just immediately as you type. So you type and you get a highlight saying, okay, this is wrong. Please fix it. You save some debugging time. It doesn't mean that you don't have to write unit tests or you don't have to write tests. It's just that it helps you to catch your errors earlier in your code. And that's valuable because, as you know, in software development, the earlier you catch the errors, the cheaper it is for the project. So another thing I heard a lot is, okay, you're missing the point of duck typing. And duck typing is just using objects not for what the type they are, but using them for what they can do. So we don't actually care about what type an object is. If it can do what we need to do, well, it should be enough. And if we start just adding types and maybe checking those types, well, we're missing the point, because the idea of duck typing is just to use something that maybe is from a completely different type or belonging to a completely different hierarchy, but that still does the thing we want to do. What I want to say is this. First, I just want to say that annotation and types annotation specifically are not incompatible with duck typing. And I'm just going to tell you more about this later, but just keep it in mind. And secondly, a lot of people say, okay, this is too verbose. The reason we use dynamic languages is because we don't want to type names all the time. And this is true for some languages like Java, where you have just to type a type name a million times. Well, this is in some way true, but one thing to remember is that annotations are completely optional. And also, one thing to mention is that in practice, dynamic languages do things like this. Oh, sorry. Like this. And what this is just they use a doc string and they start adding typing information to that doc string. And this is very common on any Python, any medium to large Python library. You will see, at least for the public API functions, you will see that they are annotated inside the doc strings. So they just not add information about just like documentation, but they also add like types. Well, this works, and in fact, I guess PyCharm does just take information from these things. But one problem with this is that it's hard to ensure that this is correct information. In fact, this example I have here is from the Boto library, which is something it's a library to use Amazon Web Services. And this documentation here is actually wrong, because the function is not going to return a bool like it says there, but it's going to return a string. I figured out that this when I was working with this library, so I decided to paste the example. So worse than no documentation is bad documentation or wrong documentation. So yeah, if you complain about typing type names is too verbose, well, the reality is that this is even more. So let's take this in account. Okay. Now, all these things I've been talking about are just a nice thing when you statically inspect Python or you make a static analysis of Python. But I'm just going to talk about something that is probably a very bad idea, but it's good for experimentation, and it's about runtime checking. And I want to stress that this is probably a bad idea. I mean, checking types of functions at runtime. The main reason is that it's slow. It might be even 200 times slower than just not doing it. It's also not very useful because checking types on runtime is not very useful because if you use a string instead of a list, well, eventually you will fail somewhere at runtime. So it's not really helpful to fail at runtime because of a time complaint. But one interesting thing about doing runtime checking is that it allows us to experiment. And for me particularly, I've been experimenting with runtime checking to explore what the possibilities of using type annotations in code. And also, maybe if we just expand our notion or our concept of types, we maybe will find that runtime checking might be useful. I will talk about that later. Okay, so first I'm just going to explain you the basic case of runtime checking. And it's basically, if you have type annotations in a code, you can have just a small decorator that basically transform that function into one that before running, just check that the arguments that you send to the function are match the ones that you're annotating. So here's a small example. We have just a test function. It has a small argument which we have annotated. It must be an integer. And the function is also returning an integer. So the idea of using this kind of decorator is that if you just use a number or an integer, well, the function just works well. But if you just pass a string, well, you'll get an exception, a type error, saying, okay, that's not the type we're expecting. And again, the warning, this is just probably a bad idea. I'm not just telling you to use this. It's just proof of concept, basically. And this is really slow. Doing this can be really slow. And how we do this, well, it's very easy. Remember, annotations are just a dictionary attached to the function. And what we can do is just, the type check decorator can just go, walk through that dictionary and walk through the list of arguments in your function and just make sure that they match. And what they use is the old isinstance function to determine if the types are correct. Now let's go back to duck typing. So you say, well, this is using isinstance is basically killing duck typing because yeah, we don't want to test if someone is from this type. We want to test if this object can do this that we want to do. But that's not entirely true, and we can do just some things with Python that can help you to have type annotation and duck typing at the same time. And this is something that TypeScript does, and it's called structural interfaces, or sometimes they call duck typing interfaces. And the idea is basically, instead of defining a hierarchy of an interface, what we do is in an interface we define what we expect from an object. So in this case I have, for example, this interface called iterable with length. And this iterable with length is just basically any object that can provide me two things. One, an double underscore iter method, so we can just iterate over the object, and a length method, so I can just get the length of that collection. And if we test this, for example, just with a list, a standard built-in list, well, it matches because a list can be iterated, and a list also has a length method, so we can get the size of the list. Same for dictionaries. You can iterate on dictionaries, and you can get the size of the dictionary. But if you try, for example, with the generator, here, well, it doesn't match because a generator is just lazy, and you can say beforehand the length of the result because you can just iterate it until it finished. And the same for a completely different object like one. Well, it's false because well, one doesn't have any of those particular possibilities. And something that I want just to remark here is that we don't have to explicitly say, okay, the built-in list implement this interface. We don't have to do that at all. what we do here is just try to inspect the element that we're passing and just check if it provides what we need to use. In this case, those special methods. Let me show you another example. So we can have, for example, a person, which is this is an interface. And I will say that that person has two properties, name and age, and it has a method which accepts a string and returns a string. Then on the other hand, we have this developer class, which doesn't say explicitly that it's implementing that interface at all. It's just implementing it. So you can see that it also has the same two properties, and it also has the same method with the same signature. Now, if we check this using isinstance, well, it's going to say they match. And that's what structural interfaces are. Okay. Well, first, something I forgot to mention is that I'm using here this interface sub class, and this is actually something that I have implemented in one library. I'm going to show you the link at the end of the talk. And I'm just going to describe you how to do this. And here we need a little bit of Python black magic. And I know it's a little bit dark, but okay, the idea is basically that if you define a meta class, you can override this instance check and subclass check methods. And what that means is that for that meta class, you can basically decide what each instance returns. So you can basically dynamically say if one object is an instance of another one using the standard built-in isinstance function. And the same for the built-in isSubclass function. So I'm just not going into the details of how to implement that. I'm just going to say that this is actually possible. And the same thing is possible from a static perspective. I mean, this is how to check this at runtime. Of course, this is even a worse idea than just checking built-in types, because this is even slower. But it's just an interesting testbed to check these things and check if it's possible to do things. Okay, now that we know that we can override this instance, we can just try to play a little bit with that concept, saying instead of checking if an object is from this type, what if we just check if this object matches this criteria? And that is what we call predicates. So basically, it's just small test functions which tell you if an object is from the type we want or not. One example, very simple example, is just a predicate which is a positive number. That positive predicate just tells us if the object is greater than 0, well, it's a positive. At least that's the simple way. Then we can use isinstance to check if a number is positive or not. I know this is just like it looks like a weird way of checking that, but the point of this is that then we can just start using that as a function annotation. For example, if we have this square root function, we can say that the argument of that function must be positive. So every time we call it with a number that is not positive, for example here with -1, well, we'll get a type error. And this is just a very simple example, but the idea of this is just having small units of behavior that we can check for in our functions. And this is very common. We have a lot of prerequisites in our functions, and sometimes we just do check that manually. With this, we can start just using them as function annotations. Okay, now more fun with predicates. We can just add more different kind of predicates to our functions. And one possibility is, for example, an options predicate, which basically check if an object is one of the elements that we pass there. This is useful, for example, for a file mode in our file open function. So we can just tell that the variable must be one of those. Instead of checking that manually, if you have to do that several times, you can just define a predicate and start using it as a function annotation in any function that takes that argument, that kind of argument. On the other hand, this is, if you just see it from a static perspective, your IDE could just take that information and also show you a nice autocomplete dialog of the different options that your function needs. In fact, the guys from IPython were trying to do something like that for just autocomplete features. Using function annotations to specify what kind of things you expect in an argument. Another few examples here is, for example, we can have an only predicate. An only predicate just check if an object, this is just like the completely opposite thing from doc typing. Here we just want to check one exact type and no more. One example here is, for example, is if we want to just to check if some argument is a Boolean, we can just use this predicate to ensure that it only checks that. And why would we do that? Because I don't know if you know, but in Python, a Boolean is just a subclass of integer. And sometimes, if you want to check if something is a Boolean and you get an integer, well, you get a true. You get isinstance is going to tell you it's true. But with this, you can just specify exactly what it is. Another thing you can do is just specify optional arguments. And optional arguments is just an argument that can be there or can be just none and have a default value. And with this instance, we can just say that is instance of something is instance of optional if it's an instance of the type or an instance of or none. And another way you can just define predicates if you need something more complicated is just to use a decorator, like here in the even predicate. And you can also some nice things that you can do is just you can start like combining predicates. So you can say, for example, that an argument must be even and positive. That's a silly example, but it can be interesting with other cases. Okay, so this is just an example of how can we just add more annotations to our open function. So, for example, the file name, we can just add a predicate that check if the name is from matches certain regex, or the mode should be one of the given options and nothing else. And encoding is optional, and well, so on. Now, another thing that it's interesting when you're starting just playing with this is that sometimes and this is specifically true for dynamic languages, is that sometimes you have functions that behave differently depending on the arguments, or that return a different value depending on some conditions. And so here you need some sort of unions. And a union is basically saying, okay, this can be or an int, or this type, or this other type. In this case, for example, number or string can be or an integer or a string. And as you can see in the test there, well, we can check different types and just make sure that every one of those objects is an instance of number or string. Then again, we can just use that in function annotations to say that a given argument is from one type or the other. One classic example is the isinstance function. This is the standard built-in isinstance function. And here, if you know, there's well, the object that you want to check and the class or the type that you want to check for. And here you can, isinstance by default just accept or a single type or a tuple of types and returns true if the object is any of those types. So here we can say, for example, that the class can be or a type or a tuple. Or better, we can do something interesting that we can do with function annotations is to refactor this in some way to allow overloading. So for example, we can, instead of just having a branch of code inside the same function, we can just create two different functions which will be called depending of the arguments that we send. For example, here we have isinstances, we have split this function into two. And the first one just is the case for a single type. I'm not showing the implementation here. But then we can just use another create another version of the function which will be called when the second argument is a tuple. And in that case, it will just check if any of the if the object is of any of the types given in that tuple. Now, something I would just want to mention, because I saw that this was just approved just a few weeks ago. It's PEP 443, alias HTTPS. No, just kidding. The idea is, it's some way of implementing this, but I don't know, with a little bit more boilerplate code. So the idea is to add this single dispatch function to the functools standard module. And the idea is just single dispatch shows you if it's a single argument, you can just implement, take that implementation for the function. But if you get, for example, a collection, so you do something differently. And the idea is just to separate logical units into different functions. So this is just function overloading. It's something that it's not, it's not possible in Python, just exactly like that. So these are just ways to overcome that limitation. And well, we can also define more kinds of types. In this case, we can see, for example, a typedef, which is useful when you want to define a function that accepts some sort of callback. That's common in like event-driven code. Like, for example, you have this mouse event, and that mouse event is usually, it must be just a function accepting, for example, an event argument. And it would be nice just to define this typedef type, which is basically a function implementing this signature. And then you can just use, in your handler, you can say that event is a mouse, is from type mouse event. And that can be checked at runtime. Another thing, well, this is actually not implemented or I haven't implemented this yet, but it's something that I just trying to think about it. It's parameterized types. And the idea is, well, if you start messing with types, you want to start doing things like, okay, what if we have like a dictionary type which uses string keys and maybe integer values, or a list of given type, for example, a list of ints, or a set of ints, well, you get the idea. Well, this is just really hard to specify. If you start just getting more and more with this, you eventually have to define some sort of generics standard or something. So this is just something that I will leave here for discussion, how to implement that. And also I want to show another approach to this, which is this interesting library called rightarrow, which basically defines something like a small language just to define types. So instead of using explicit types, as I've been doing as annotations, because remember, annotations can be any kind of object. Instead of doing that, this uses just strings. And these strings represent different kinds of types. So you can just have named types or regular types like integer or long or float or complex or a class name. But you can also define some sort of, for example, you have a specific syntax to define unions, which is with the pipe operator. And you can have also define parameterized types like tuples or lists of even, for example, complete dictionary schemas and things like that. It's very interesting. I'm going to show you the link to this library after. And of course, it also allows you to implement different sorts of like function specifications, like for example, a function taking a string and returning an int, or a function taking two ints and returning an int, and so all kind of different combinations. It's just a whole language for this thing. So this is an interesting approach to that problem, which I would like to mention. And how this works? Well, this library is actually Python 2, so it doesn't use actual annotations. So what it does is just, it has this guard decorator to just do runtime type checking. And what you pass is the spec of the function. For example, here it's a function that takes a Unicode in Python 2 and returns a string. Of course, we can just, if we use, we try to translate this to Python 3, we get, in my opinion, a nicer syntax with annotations. So you can just say that safe encode just take a string and return bytes, and it's it's cleaner, in my opinion. Okay, this is just about types. Another, of course, because Python, in Python you can define any kind of object or any kind of expression as an annotation for a function. You can have other uses, not only type annotations. And this is just the small example I showed you before, but which a little bit more of detail, which is basically you can use Python annotations to add docstrings to each of your arguments. What we see often is that this is done, as I showed you before, this is done inside docstrings. But in my opinion, this is a much closer to the value way to do it. And also you don't have to repeat argument names, which often have mistakes. And also, if you, for some reason, you change your API and you want to delete a method, well, it will be easier just to get your documentation attached to your actual code so that the documentation reflects what it's actually there. And when you start using annotations for other things, not only types, well, there's a question, and it's how do you make two different kind of annotations just play away with each other? And this was actually an interesting discussion in the Python ideas mailing list, because the IPython guys were trying to use Python annotations to just add auto-completion features. And the question was, okay, we're using annotations in this way, but how can we make sure that we're not going to mess with other people using annotations in this other way? And after some discussion, I think the BDFL said, okay, let's just try to start using this this pattern, and let's use a tuple for our annotations. So if we want to add many annotations to a single argument or a single return value, well, let's start just putting in a tuple. So in this case, for example, I'm just using this compile function, and I'm adding two kinds of annotations, one for the type and one for the documentation. And if we want to add another thing, well, just add it. And the decorators or the thing using the annotations for actual things, well, must be sure that an annotation must be a tuple or must be a single value, and it should just try to find the one that is right for it. Another use I want to mention about annotations is just to create language bridge. And this is just a small example I was playing with, and is how to define methods or functions that are imported, are native functions, and are used using the C types module. So in other words, just how to use C functions from Python easily and just make an automatic conversion of the types as you need. So here, for example, we're using the standard C library string char function. And here with annotation, we can say these arguments, which kind of C types they are. And after that, we can use the C types functions to translate that and just define the functions for ourselves instead of doing that manually. That's perfectly possible. Another interesting example is just to, sometimes you want to, for example, for object relational mappers, you want to map some specific types to some database types, and you want to make sure that they're correct. So you can use annotations for that. This is another use case for this. Okay, finally, because I'm running out of time, I want to discuss a little bit about why this feature is not widely used, or why people are not using this. And I've been just reading a lot of Python libraries and trying to find someone using it in some way, and there are just very few examples of it. Very experimental things using this feature. And I think one of the reasons is, well, first, it's not a wide-known feature. As I said at the beginning of the talk, there are a lot of experienced Python developers who don't know at all about this. And second reason is that this is, of course, Python 3 only. And even now that we have a lot of important libraries being ported to Python 3, Most of the time, this still wants to be. They try to keep backwards compatibility, so they want to keep. They usually try to keep a state where they can be useful in Python 3 and Python 2. So they're not going to use this. And another reason, which was discussed also on the Python ideas mailing list, is that this brings too much flexibility sometimes, and because of you can put any arbitrary expression as a function annotation, so people often don't know exactly how to do, or they don't know the Pythonic way of doing it, so it's not defined, and so people just decide not to use it. But the idea is just, or my invitation with this talk is just to start thinking about this, and just to start we don't know what is the Pythonic way of doing this, and what I've been showing here is not exactly the way to do it, it's just some way I've been just thinking about. And it would be nice just to start discussing this, and just to get and construct the Pythonic way of using this feature, because I think it might be useful for developers. And of course, some use cases I think are not complete. The original idea, or why this feature was added to Python, is because the BDFL wanted to had the idea of adding optional static typing for a long time. You can see that in some blog posts, and you can see that there's an idea going around and around. And this was just some way of starting doing that in some cases, but it's incomplete. So we only have function annotations, but we're lacking like a proper interface definition. We're lacking a way of defining parameterized types. We're lacking we're missing a lot of features that we need for actual static, optional static Python in static typing in Python. And this is something that one of the reasons why this is actually not used, but we can start just constructing that as well. And that's my invitation with this talk. And because there's nothing done with this, so sometimes you don't see the immediate benefit of doing this. So IDEs most of them don't support already this static analysis. Runtime tools like the library I showed you before are not exactly ready for production, or even they're not a good idea for production. And so you can start adding annotations, but you don't get a benefit from that. So my invitation is to start just doing things that can help us to start using this. And finally, I think that's it. Before asking questions, I just want to say that the small examples that I showed you before are part of this library called type annotations. The rightarrow language for defining types, it's called rightarrow, and it's in this link. And if you want to read the PEP for type annotations are in this link. So apart from that, let's go ask some questions while I eat ice cream.
Thank you.
Thanks.
The third thing I was wondering, I was curious about the type check decorator you showed before. How is it going to handle the something like a recursion list? You know, the list inside itself. Have you tried with that? It's not in the standard library, right?
You mean the type check decorator? No, that's not in the standard type library. That's in this library that I'm showing you here.
Type annotation, okay.
What do you mean by a recursive list? And
a equal list, a dot append a.
Okay, yeah, that's actually a pretty good question. Yeah, that's one reason why we don't. I say that we don't have this feature is not. Annotations are not complete for bringing static typing or optional static typing to Python. The thing is, annotations are evaluated before. While you're just actually executing or reading the definition of the function. So if you point in the decorator, in the annotation, something that it's defining inside the function, it's not going to be possible because it's going to be undefined. But there are some workarounds there. For example, that's the case for example, when you want to define an interface which points to the same interface. Like, for example, a tree. A node has 2 pointers to other nodes. So how do you do that if you define if you haven't actually defined what a node is, because you're actually defining it there. Okay, sorry. So the workaround is just to have some sort of beforehand definitions of what you need. And actually in the library there are some examples about that. So you basically define like a typedef or just an empty thing that you can just reference. And before doing the static analysis, the recursive analysis, and once the thing is evaluated, well, you just replace thing at runtime. I'm going to show you, well, if we have time, I'll show you an example of how to do that. Any other question?
Could you please jump back to the slide about overriding functions?
Yep. Oops. I think it was here. Nope. Okay. This one is.
Okay, so for example, when you have more than one predicate matching, what's the order of calling them?
Well, the idea with, it doesn't matter actually, because the idea with overloading is that you take the signature of the function, and eventually the first thing you do when running the function is just checking the arguments. If you, and depending of which kind of arguments, for example here in this instance, you check t. If t is a single type, you just go directly to the first definition. If t is a tuple, well, you go to the other definition, so and so on. So you check the signature and you just choose the one that matches. If you have two signatures that are the same, well, that's going to throw an error.
So that's not in the way that this first one wins, right? So it will throw the
yeah,
error,
no,
right?
I mean, it's not, it doesn't matter because it's just a branch and all of them just, I mean, it's not that we execute one and then the other, but we only execute one at a time. So we just have to decide which one, depending on the signature of the function.
Well, one thing which I would like to see, maybe if it's possible, is some kind of duck type checking, if that exists. So something like be able to check automatically if an object has an attribute, for example, without doing if as at, or just doing the normal duck typing things. So is that maybe something that's possible? Because I don't want to specify the type directly. Maybe I want to keep it more free. I just want to have a collection. I don't want to have a list, for example, because a tuple.
You mean like to see if it's a or not?
Yeah, something like this, yes.
I don't know which model is, but how was called the model for checking? Was iterable, callable, or ABC?
There is this abstract-based classes, or ABC for short.
Yeah.
That try to do that.
I know that, but in a way like this with type check, the decorators and these kind of things, but for
you can actually use a abstract-based classes here as a type annotation. What I don't like about abstract-based classes is that when you define an abstract-based class, you still have to explicitly tell which subclasses or which object implements that. So if you go to the abstract-based classes collection module, you will see that there they say, okay, a list implements a collection, or not that implements, but collection registers subclass and just the built-in list. You still have to manually do that because abstract-based classes are not able to just check if the object provides what you need. You still have to tell it manually, and I don't like that about abstract-based classes. But you can use them here if you want. Okay. But if for some reason you have this crazy thing that implements the same as abstract-based classes, well, you have to register that type manually in the given abstract-based class.
Sure. And I think I would like to use something like this, but only if it really makes my life easier and actually makes my code faster, for example, which is what types are supposed to do, I think, in another kind of language. But it looks like in Python is the opposite, because as extra check has more runtime work. So I'm not sure.
Yeah, well, that's another use case. Here, I was just talking about runtime checking, but Well, in theory, and I said this really in theory because it's really hard to do, and I just don't think it's feasible, at least with CPython. You can just make your code faster if you know, you just perform some static checking at compile time. And this is something that some languages that try to do this, like Dart, for example, which is this Google JavaScript, this language that tries to replace JavaScript that Google is doing, does that. It uses optional types, and if you provide types, it's going to help you with that. So in theory, it's possible just to, with these annotations, make the interpreter just make assumptions about that and just optimize. But I think that's really hard to implement right now. That's why I didn't mention anything about that. But maybe with other kind of implementations like PyPy or maybe, I don't know, Jython or IronPython or something that are closer to a typed specification, maybe that might help. But in this case, it's just something that I don't see possible in the near future. So I would like to say that, yeah, runtime thing is slower, but the potential of this is, for me, is just a static analysis where you don't actually run this, but you make your editor or your IDE just get information about that and help you to be more productive.
Mine is mostly a remark. Are you familiar with C++ concepts?
Yeah, a little bit.
Because there's a very strong analogy between your structural interfaces and C++ concepts, and the whole idea of checking duck typing. Well, in C++ it's for templates which are a form, well, support a form of static duck typing, and to check the properties of the types that you pass in to ensure that your template will instantiate correctly or provide a sensible error message.
Yeah, that's true. But I will have, yes, C++ it's true, but I prefer just, if we're just trying to do an analogy with other languages, I prefer something like Go, for example, where you can define an interface, but you don't have to explicitly say if something implements that interface. It's not mandatory. And you can just, the runtime or the compiler is just smart enough to understand if something implements that interface. The same happened with this TypeScript language, which does exactly the same thing. You define an interface, and you don't have to say this class implements this interface or this object implements this interface. The compiler is just smart enough to know if that's the case. But yeah, it's similar. Just that for me, the C++ template language is just, well, it's kind of overwhelming. And of course, it's also very powerful, but yeah.
Yeah, so I also have a remark. So just wanted to make this clear that PyCharm does support all of this stuff for specifying types in annotations. We are also very disappointed that no one uses that. And
thank you.
To make this easier to use, we actually have quick fixes that let you put these annotations. So for example, if we are able to infer the types from somewhere, you can press Alt-Enter and it will put the type into the annotation. And so hopefully this will drive some more people to use this.
Cool.
Comment on the comment maybe. Yeah.
Oh, yeah.
You can comment on the comment. I think in the PyCharm it is only supported for the documentation-based annotations, right?
No. Python 3 annotations are also.
Okay. Okay, cool.
He's a developer of PyCharm, so I believe him. Also, well, something I would just like to mention, and I didn't because I forgot, is also there's this cool library for autocompletion called Jedi. I don't know if you have used it. It's just a simple library that you can use with any editor like BI or Emacs or Sublime. And there's also working process to start putting this, but there's also an ongoing discussion about what should be just the conventions. And that's something that we have to agree on, because there are different approaches, as I mentioned. One is just using this rightarrow language, for example, and another one is just to use actual type objects. So that's an ongoing discussion, and we expect to add that feature to Jedi someday. Any other?
Hi, thanks for the talk. I want to know, personally speaking, since type checking is so slow, as you said, what's the main benefit you get from using annotation? For documentation, for type checking?
If you ask me personally, the main motivation for adding is just helping the tools to help me. So yeah, to just highlight errors quickly, to show me auto-completion details, to allow me to refactor easily and in a way that it works correctly, reliable way. So yeah, that's for me the big deal. It's something that is not, well, it's maybe there yet, now that we know, but it still needs some more use from the community, I think. Anything else?
Hi, are you discussing parameterized types?
Sorry?
Are you working on parameterized types? So, for example, you have a list of anything, as long as it is the same type in the list, for example.
Yeah, we're finding, we're discussing, but this is very complicated because once you start messing with parameters type, you get like a sea of things that you must implement. So the initial approacher always have like drawbacks. So this is still something like we want to design, and the language, of course, doesn't provide anything just to deal with this. Something that you have to come with a convention about how to do it. For simple cases, it works, like, okay, a list of ints. But sometimes this can be a lot of things. It can be when you start talking about, for example, dictionary schemas for saying something. Well, what if you have a dictionary whose keys are string and values are other dictionaries which blah blah blah. So that's kind of hard, and it's something that it would be nice to have some language support for it. But right now we're just discussing what is the best way to do it. There is one just like here. It's just some proposals. It's to have this kind of small functions like typedict, where you can define a schema of the dict, or just a type sequence, or just a type sequence where you can define the exact sequence that you want, in this case a set, and which kind of types you need in that. But of course, as I said, it's not that easy. It's something that requires thinking and designing.
Oh, okay. Unfortunately, it was the last question. So thank you. Should be the coffee break now.
Ravioli finito. Can you please show me the stuff? Oh.
Yeah.